So today we are going to do an experiment on a Lego kit, which is kind of a toy kit, and it has a programmable block which allows us to program it like a robot. So the version which we have is called Lego Mindstorms NXT. There is a newer version of it called EV3, but right now here we have a NXT version of it. And Lego is basically a toy company. So it started off as a toy company. Now it is also bringing up mechatronic toys. Okay, so we have one such kit here. So we'll be doing some experiments on it. There are various ways in which you can program this Lego kit. So the one which we will be using here is SIMULINK. Lego itself has an interface, a block-based diagram by which you can program it. Then LabVIEW also provides an interface to program this Lego kit, but we'll be using MATLAB interface or the SIMULINK interface. So MATLAB 2013A onwards, they have provided a hardware support package in which you can download and use for programming this Lego kit. And a Lego kit looks something like this. So it has a central brick which is programmable. This brick has an ARM processor inside. So whatever program you have to write, you can write on this. This gets connected to the CPU by a USB cable, we'll see that. And it has 3 ports for actuators. So these are the 3 actuators. And it has 3 ports for, it has 4 ports for sensors. So there are various kinds of sensors. This one is a touch sensor, this one is a sound sensor, this one is a light sensor, this one is an ultrasonic sensor, and these 3 are the servo motors. Okay, and this is the programmable block which takes in input from the sensors and gives out output to the actuators, and in between we can do some processing here. So we will be using this MATLAB interface for programming this. So to start programming this, we will just open the MATLAB. Okay, so it has to be 2013A onwards, so we have 2013B, and you have to install the hardware support package for Lego Mindstorm NXT. If you do not have it right now, you can install the hardware support package by going to add-ons. Then you say get hardware support packages, and then it will guide you through how to get the corresponding support package. Okay, so maybe we'll not complete the procedure here. So we say download from internet and say next. Then it will show a number of available support packages which is there in MATLAB. So you can complete this procedure. It will give a list, then select Lego Mindstorm NXT, and then you go ahead. So here, from here you can select Lego Mindstorm NXT and install it. Okay, so I'm just closing it right now. We have already have it installed here. Now we are going to use SIMULINK for programming this NXT block. So we just say new, and then we say a new SIMULINK model. So this is the empty SIMULINK model which I have opened. I'll also open the SIMULINK library browser. So have you used SIMULINK before? You have used it. So in SIMULINK you have many blocks. Basically you can make your program by combination of blocks. So what what we are going to use to program this Lego is a library which has support packages for the hardwares. So what are the hardwares? The sensors and the motors. So the Simulink has provided one library which has support for Lego hardwares. So this is the thing that we want: Simulink support package for Lego Mindstorm NXT hardware. You click on that, you will see many options here. All the hardwares of the Lego are here. So right now, if you see, we have two light sensors attached to it, okay, and we have two motors attached to it. Fine. So if you just bring other sensors also. Yeah. So this is the touch, this sound, that is ultrasonic, this light. So suppose I want to make a simple program. So let us start by something like I bring this LCD here. So LCD is for the display, and then I bring this touch sensor here. Okay. Now I say I attach the touch sensor to one of the ports here. Okay. So here the bottom ports are for sensors, the top ports are for motors. Okay, the sensor has to be attached at the bottom port, which are named 1, 2, 3, 4. So I attach them to one of these ports, port number 3, touch sensor. I connect these. Okay, if I double click here, I will get a description of what this LCD block does. Okay, so you'll get a description here. It basically says that this LCD block, it displays the numeric value which it is receiving. Whatever numeric value it will receive, it will display it. You can choose the line number on which you want to display it. You can give a label. Suppose I give a label called touch. So I can give a label. What this touch sensor does, it outputs either 0 or 1. Okay, if it is pressed, it outputs 1. If it is released, it outputs 0. So what do I expect this program to do? So if I load this program on Lego, on the screen, 1 or 0 will appear. If I press it, 1 will appear. If I release it, 0 will appear. So to put this program in the Lego, I need to go to Tools. I go to Tools. I say Run on Target Hardware, and I say Prepare to Run. So it asks me what is the target hardware. There are various options. We want Lego Mindstorm NXT. Then it says what is the mode of connection. So we have USB connection. Say OK. Now this is the button to deploy it to hardware. Okay, so I just click it here. So I've connected it. It is switched on. So it will be the program will be written into the processor here.
Nobody knows the password of that country.
Okay. So it has written this program into this. Okay, now it is running on this. So if you press the touch sensor, you will see the output changing. It's not changing because I have made a mistake here. I have attached to port number 3, but port number 1 here. So I will have to change this. So we have to select port number 3, and then I again deploy it. So I will have to stop this program and switch it on again. Then I say deploy. So now it will show. Okay, so simple program. So it is so easy with this, don't you feel that? I just had hardwares here. I can directly easily program it and deploy those programs here. It becomes, where is the program? So MATLAB converts this block diagram into a program, a C program, and it puts into this ARM processor. So we don't have to bother about that. We just have to know how I make this block diagram, what is the logic I am putting in this block diagram, that's it. Okay, so that was one. Yeah, that's why they have provided this interface to make things easier for those working on robotics, so I don't have to worry about what kind of sensors and all those calibration and everything. I can just start working with my algorithms. Okay, now let me bring a motor here. So in this I also have a motor block. Let me bring a light sensor. Okay, so I make this kind of a connection. So let's see what motor block does. So to know what a block does, we just double click it and a description opens. So it controls the power and direction of the motor. The input port value can range from 100 to -100. Okay, 100 is maximum speed in maximum power in one direction, -100 is maximum power in the other direction. So what it does is it takes a numeric input, and if that numeric input is of larger value, larger power, you know, it does not map directly to the RPM or anything like that. It simply means if you input a larger value to this, it will apply larger power. Then we can see what light sensor does. So this light sensor, it senses the light. So there is, if you see here, there will be an LED. There is an LED and there is a detector. Okay, so if you have some surface, LED will incident some light on that surface. It will reflect and the detector will detect it. Okay, now it outputs value between 0 to 100. Higher the intensity of light, more the value. Okay,
So what is the range of light sensor?
0 to 100.
How many distance it will?
Distance doesn't matter. Whatever light it is receiving, if it is bright light, it will give a larger value. If it is faint or if there is darkness, it will give lesser value. So if I keep it like this, it is receiving some ambient light, right? So whatever intensity of light it is receiving, it will give that much value. If I take it near that tube light, it is receiving more amount of light, so it will give a larger value. Now it will give a lesser value. If you flash light on it, then it will give larger value. That's it. Similarly, there is this sound sensor. It also works like that. If it is receiving louder sound, then it will give a larger value between 0 to 100. This is range sensor. So this gives output in centimeters, between 0 to 255 centimeters. So how distant your object is from this sensor, it will directly give you output in centimeters. So the activity that we are going to take up today is using Lego for a line follower robot. So this is the kind of setup that we are using. Here is the Lego robot that we have assembled using the parts of the Lego kit. Here is the programmable block, the two light sensors which are attached to ports 1 and 2, the two motors here. There is the first motor attached to one wheel, there is a second motor attached to another wheel. They are used using port A and B, since we have two different independent motors, for each wheel we have a differential drive, and by changing the relative speeds of the motors we can make the robot turn left or right. So and this is the white background on which there is a black strip which the robot is supposed to follow. So there is a simple line follower kind of robot. And if we want to think about how this robot can follow this line, so let us for a moment imagine that we are seated behind this robot and we are looking this way. So this will be the right light detector or light sensor. This will be the left light sensor. There is the right motor and there is the left motor. So or here also we can see there is the right light sensor, there is the left light sensor, right motor, left motor. Now if I want to follow the line, the logic is simple. If the right light sensor is above the black strip, then I have to move right. In that way I will have the robot follow the strip. In a normal position, you can see here both the light sensors are on the white patch. So both the light sensor will be receiving almost equal amount of intensities, and therefore the values which they give to the processor will be almost equal, which will be corresponding to the white surface. And when one of the light sensor goes over the black surface, then we will have a smaller value being sent by that light sensor to the processor, which will mean that there is a difference between the value of the right light sensor and the left light sensor, and we'll use this the difference in this value to turn the robot. Now a very straightforward logic here is whichever if the right light sensor is on the black strip, then we have to turn right. If the left light sensor is on the black strip, then we have to turn left. Is not it easy to see that? If the right light sensor is on the black strip, we have to turn right. If the left light sensor is on the black strip, we have to turn left. Okay. Similarly, if there is a curve here, there's a turn here like this. For this turn, as the robot moves forward, the left light sensor will remain on the white, whereas the right light sensor will go over the black. So that will imply that the robot has to move right. So always it is the case that whichever side's light sensor goes over black, one has to turn to that side. So right light sensor goes to black, one has to turn right. And from the very nature of this light sensors, when the light sensor senses a lesser intensity, it gives a smaller value between 0 to 100. So in a very natural way, if it has to turn, if the right light sensor is over the black strip and it has to turn right, the right light sensor will give a smaller value between 0 to 100, and we can feed it directly to the right motor. The left light sensor will give a larger value between 0 to 100, and we can feed it directly to the left motor, and therefore because the right motor's speed is lesser than the left motor's speed, the whole robot will turn right. Now let us see this simple logic implemented in this block diagram, SIMULINK block diagram, using the Lego Mindstorm NXT hardware support packages. So we have the right motor the left motor, the right light sensor, and the left light sensor. So simplest, most simplistic design of line following logic is that directly give the output of the light sensor to the motor. But as we will see, this kind of a logic will not allow the robot to take sharp turns which are required to be taken in this kind of a scenario which we have chosen. Therefore, we need a better algorithm for line following, and this is the one which we have proposed and implemented in this Lego for the line following. Here you can see so here in this block diagram we will see how this block diagram will allow us to maneuver our robot along the black line more effectively. So the basic logic remains the same. Whichever light sensor is giving a lesser value, that is, it is over the black strip, we have to turn to that direction. Right light sensor gives a lesser value, it is over the black, turn right. Left light sensor is over the black, turn left. So this is the logic which remains the same. The only thing that has to be tuned is the amount and the sharpness of the turn that we have to obtain. So now let us look at this block diagram. In this block diagram, just forget this difference gain for a moment, or let me just remove it altogether. And I'm opening the SIMULINK library browser so that I can bring it later. And I will just connect these two. So yeah, so suppose the right light sensor gives me a is over the white, the left is over the black. Left will give a smaller value, right will give a larger value. The difference will be positive, and this positive difference, this is fed to these two blocks. One is an add block and one is a subtract block. So we know that if the difference is positive, the right motor should move at higher speed, the left motor should move at lower speed. So the difference is positive, say it is plus 10. So this plus 10 will get added by this constant. 30 plus 10 is 40. The 40 goes here, and okay, it has come. And also 10 goes to this block, so here is a constant 30, and 30 minus 10 is 20, so 40 goes here and 20 goes here. The difference between the value that is going to these two motors is 20. So this 40, this is 20, and so the whole robot will move towards left. The very fact that right motor is moving at a higher speed, left at a lower speed, means that the whole robot will turn towards left. And we have added this LCD display so that we can see what is the different amount of power that is being given to each motor. Now fancy a scenario in which the right light sensor is over the black line and the white is on the white, and the left sensor is on the white. So this difference is negative. Say it is minus 10. So 30 minus, or rather 30 plus minus 10 is 20, goes to right motor, and 30 minus 10, that is 40, goes to left motor. Therefore, since the left motor is rotating at a higher speed than the right motor, the whole robot will turn right, which should have happened because the right sensor is over the black line. So that's it. That's about the logic which we are using. Now these constants 30, what effect do they have? These constants have the effect of increasing the net traversal speed of the robot along the strip. So if I use 40 here, 40 each here, I will have values coming here like 50 and 30 or 30 and 50. The difference always being the difference between the value of light sensors when one is on white and another is on black. So if that difference is 10, then the difference between the powers which are going to each motor will be 20. Now there is a way in which I can increase the difference between the power that is going to each motor. Why do I want to do that? I want to do that because I want to increase the sharpness of the turn that I am taking. So if I want to increase the sharpness of the turn, the power or the speeds of the two motors should be as different as they can be. So the larger the difference between the speeds of the motor, sharper the turn that I am taking. So now I go to my SIMULINK browser and go to sources and bring this constant here. No, not this one. I have to bring a gain here. So I will bring a gain here. Yeah, here it is. And I have to attach this gain in between. By doing so, I'm giving this gain say 2. By doing so, I magnify the difference between the value of the light sensors. So if it was 10 before, after this gain it will be 20. So the difference between the powers that are going to the right motor and the left motor will be, the maximum difference will be 20 now, 40 now. Yeah. So earlier it was 10, the difference was 10, and the difference between the power was 20. If the difference is 20, the difference between the powers will be 40. So this gain helps us to regulate the sharpness of the turn that I am taking. These constants here, they regulate the net or the traversal speed of the robot along the strip. So if we choose to have a large traversal speed, there can be a problem that the robot can easily overshoot the strip that it is following. So we have to regulate this traversal speed constant and the sharpness of turn constant, the gain, in such a way that our robot does follow the line that it is supposed to follow. And we have also given a small video which will illustrate how our robot performed for line following with this algorithm. So just have a look at it.
What is effect behind? Being still.